Welcome to the e-Pathshala lecture series in computer science. We are dealing with the course computer architecture. This module we will discuss about the handling. So, the objective of this module is to discuss the handling of data hazards in detail. So, previously we looked at the various types of data hazards. We pointed out that you may have data dependencies and name dependencies. So, data dependencies, you can have a true data dependence which will give rise to what is called a raw hazard, and you may have a name dependence, either an anti dependence or an output dependence. Anti dependence will give rise to a war hazard, and output dependence will give rise to a war hazard. A war hazard and war hazard are basically caused by name dependencies, and because they are only name dependencies and you do not have true data flow between them, they can be easily resolved by register renaming. But in the case of a raw hazard, this will give rise, this is caused by means of a true data dependence between instructions. And also one more thing that you will have to remember is, all these dependencies are properties of programs. You can never do away with these dependencies. But whether these dependencies will turn out to be hazards will depend on how these instructions enter the pipeline and that they get executed. So, our idea is to avoid these hazards happening. The dependencies will be there, but make sure that these dependencies do not turn out to be hazards in the pipeline. So, we look at solutions for these data hazards now. So, this is an example of the data hazards that we discussed earlier. So, you have the first instruction which writes into R1, and only during the fifth clock cycle it writes into the register file R1. But the subsequent instructions, all the subsequent instructions, the second instruction needs the data here, the third instruction needs the data here, the fourth instruction needs the data here, and the fifth instruction needs the data. So, only the fifth instruction will get the proper data, all other instructions have problems. So, this is a typical example of a data hazard, and we will see how to handle this problem. The most dominant solution that is used for handling data hazards is what is called forwarding. The other name for forwarding is short circuiting or bypassing. Now, what you mean by forwarding is, when you execute an instruction, you know the result is available somewhere in the pipeline. So, even in the earlier case, the execution is over, the result is available somewhere, but it has not been written into the register file. So, if you are able to forward that result from that place to the input of your execution unit or wherever it is required, that can solve your data hazards problem. So, that is why the technique is called forwarding. It is also called short circuiting or bypassing. So, if you want a formal definition for it, forwarding is the concept of making data available to the input of the ALU for subsequent instructions, even though the generating instruction has not got to the write back stage in order to write to the memory or registers. So, this is an example here. So, as I pointed out, you have this instruction, the first instruction has finished execution, it has still not written to the register file. So, once it finishes execution, it is going to write into this buffer, which is your EXMEM buffer, the buffer between your execution stage and the memory stage. Now, if you look at the second instruction, it has finished its fetch operation, it has finished its decode operation. So, during decode operation, we normally assume that not only decode happens, but also the register reads happen. It is fine, it has already read the registers R1 and R5, but you know that R1 is not the correct value that it has read, because R1 is a dependent register. Now, when it goes for execution, you can't use the old value of R1 and R5, but you know the new value of R1 is now available in this buffer. So, from this buffer, if you are able to forward the data to the input of the ALU. So, instead of taking the data from the conventional path of this register, which is not possible, you take it from this buffer where the data is already available and pass it to the input of the ALU. And because you forward the data from this path, it is called forwarding, you bypass the conventional path and take it from here. So, it is called short circuiting or bypassing. So, that is what is meant by forwarding. Similarly, as the instruction proceeds during the next clock cycle, this instruction which you want, the data R1 which you want, has moved from this buffer to the next buffer. because this instruction has moved from the execution stage to the memory stage. So, the memory stage is over and it writes into this buffer, which is your memory write back buffer. So, the next instruction has to take data from the memory write back buffer. So, the immediately next instruction needs data from the ex mem buffer. The next instruction takes data from the mem write back buffer, and when you look at the subsequent instruction, the first instruction has already done a write. We always assume that writes happen during the first half of the clock cycle and reads happen during the second half of the clock cycle. So, making that assumption, R1 has already been written during the first half of the clock cycle, which this instruction can read during the second half of the clock cycle. So, this instruction does not have a problem. Only the second instruction and the third instruction have a problem, and forwarding can definitely help solve this problem. Last instruction XOR, of course, you do not have a problem at all, because your register reads only come after the fifth clock cycle, that is in the sixth clock cycle. So, this is basically what is meant by forwarding. So, as soon as a result becomes available in the ALU, just read it from either this buffer or this buffer and use it for the subsequent instructions execution. So, if a forwarding path has been provided, you find that the correct results will be available and you do not have to stall your pipeline. You can avoid the stalls that have to be generated in your pipeline. Now, what are the hardware changes that you will have to bring in for forwarding? How do you forward the data from one place to another place? You already know that there are two paths going to the ALU. You have a multiplexer with two inputs. One input comes from the register file. This is a register file. The other input comes from the next PC value, which is used only for branch instructions. That is one input of the ALU. If you look at the second input of the ALU, you find that one input comes from the register file. The second input comes from the sign extended immediate operand. So, that distinguishes between a register instruction and any other instruction. So, you already have a multiplexer incorporated at the input of the ALU, because you will have to choose one among these two. Now, the moment you introduce forwarding, you know that you will also have to have data being transferred either from the ex mem buffer or from the memory write back buffer. So, you will have to add those forwarding paths. So, if you add those forwarding paths, you find that one path is added from the ex mem buffer. So, if it is the immediately next instruction which is dependent, then you will have to take the data from the ex mem buffer. So, this path is added. If it is the third instruction that you are talking about, then the first instruction has already moved on to the memory write back stage. So, you find that the data will be available in the memory write back buffer. So, you add one more forwarding path. So, your multiplexer has simply been expanded here. You find that the multiplexer, instead of having two inputs, each of these multiplexers have 4 inputs now. They have been expanded, and the control logic will decide which one of these paths will have to be chosen. So, all these options are available: reading from the register, reading from the next PC value, taking from this buffer or taking from this buffer for this multiplexer. Similarly, here reading from the register, an immediate operand here, reading from this buffer or reading from this buffer. All these 4 options are available, and depending upon the dependence between these instructions, you will choose any one of these options. Now, look at a different sequence of instructions. Let us assume that you have a load instruction. The load instruction loads from some memory address here 0R2 into your register R1. Now, that data access happens only during the 4th clock cycle, because the data access only happens here for your load instruction. So, the data comes to the processor only in this clock cycle. Now, if you look at the next instruction, a sub instruction which uses R1 as a source operand. Now, in this case, the second clock cycle, the sub instruction gets decoded and it reads its registers. It will read R1 and R5, though R1 is a wrong value. The third clock cycle, it will have to go in for an execution here. It can't use these values for execution because it is wrong, and anyway it can't take the data that can be forwarded also, because the data itself is not yet available. Only at the end of the 4th clock cycle the data comes to the processor. Once the data comes to the processor, you can provide a forwarding path from anywhere and get the data, but the data itself arrives into the processor only at the end of the 4th clock cycle, and during the 4th clock cycle itself you need it for the ALU operation, which is not possible. So, whenever you have a load instruction and you have a dependent arithmetic operation, you know that forwarding is not going to help you. You will definitely have to introduce one stall to handle the load instruction. But subsequent instructions you can always look at a forwarding path. If you look at the AND instruction here, the subsequent instruction, anyway the load is over, it is available in the mem write back buffer. So, it is possible to provide a forwarding path from here to here, and this forwarding is possible. But between these two instructions no forwarding is possible, and you will definitely have to stall the pipeline. So, this diagram indicates how a bubble has been created. So, you have a bubble created here, so that one stall is introduced into the pipeline, and then the execution gets continued in the next clock cycle, and by then your data becomes available in the data memory. You can forward it from there and continue your process. And because this instruction undergoes a bubble here, the subsequent instructions also will get delayed in their respective stages. So, this instruction gets delayed in the execution stage, the next instruction will get delayed in the decode stage, and the next instruction will get delayed in the fetch stage. So, this is again another way of representing it. So, this is the first case where you do not assume any problems. If you try to allow your pipeline to go as such, then it will definitely give you wrong results which you are not permitted to do. So, if you do not stall your pipeline, each one will go through the phase in subsequent clock cycles. So, that is not allowed in this case because of the dependency here. So, when you have a load instruction, automatically you will have to produce a stall for the subsequent instruction, and that stall propagates to the other stages also. So, you have a stall everywhere. Now, without forwarding, what will happen is when you have an add and a sub, which is a dependent sub, if you do not have this technique of forwarding, then what will happen is this is your add instruction and you can't allow your subsequent instruction to proceed. You will have to introduce bubbles in your pipeline. So, bubbles are introduced, you have one stall generated here, another stall generated here, and only then you go in for the next instruction. So, only then you will get the correct results, because only when you have a write back happening, the first half of the write back, the register write happens, and the second half of the write back you can go and read the register. So, if you do not have a forwarding path available, then two bubbles will have to be inserted or two stalls will have to be inserted, and only then we will be able to read the correct data. Now, with forwarding, you know that from the execution unit, from the execute memory buffer, from this buffer, you can forward the data to the input of the ALU, and you can go ahead with the execution of the instruction, the second instruction, without introducing any stalls. The same thing shown for a load and load use data hazard, a load and a dependent arithmetic instruction. So, for the load instruction, the data becomes available only here. So, what you do is you will have to have a bubble here, and at the end of one bubble itself, you know the with the forwarding path, once the data becomes available, you can forward the data from the memory write back buffer to the input of the ALU and go ahead with your load instruction. But this bubble, it is not possible for you to remove this bubble. One stall becomes compulsory when you look at a load and a dependent arithmetic instruction. Now, this problem can also be avoided using proper code scheduling. So, the compiler can try to look at reorganizing the code, or at the hardware level when you try to do a dynamic reorganization of the code, it is possible to separate the two dependent instructions so that they do not cause a problem in the pipeline. Say for example, here I have a first load instruction, I have the second load instruction here, the second load instruction, and following the second load instruction you have a dependent add here. Dependent add, this dependent add is, you cannot execute this dependent add because it is dependent on the load. Now, instead if you try to shift this load instruction here, you are doing a reorganization of the code. So, by the time the dependent add comes in, this dependent add comes in, you know the load has already executed, and with forwarding it is possible to solve this problem. So, the original code where it took 13 cycles for execution, you find that the reorganized code only takes 11 clock cycles for execution. So, it is possible to avoid these hazards by reorganizing the code and doing proper code scheduling also. So just recall that the dependencies are always there. As I pointed out earlier, data dependencies are properties of programs, but whether they will turn out to be hazards depends on what happens in the pipeline. So though there are dependencies, by using forwarding you can make sure that they do not turn into data hazards, or similarly though there are dependencies, by doing a reorganization of the code you make sure that these dependencies do not turn out to be hazards. Look at data hazards in ALU instructions. Look at this sequence. So you have the sequence, can you resolve these hazards using forwarding? So we've already seen that though all these are dependent instructions, they can definitely be resolved using forwarding. Now how do we detect when to forward and how to forward? So that is what has been discussed here. So you know that the forwarding can happen from here, the forwarding can happen from here. So the blue lines indicate the conventional flow and the red lines indicate the forwarding paths. So this is how you will have to forward. Now how do you detect when to forward? So if you look at the conditions that need to be detected for forwarding, we will just use a convention here. Say for example, IDEX.register RS indicates register number for RS which is sitting in the IDEX pipeline register. So if you look at the condition for forwarding, you will have to make sure that the destination register of the first instruction and the source registers, any of the source registers of the subsequent instructions do not match. If they match, you know there is a data dependence. So that condition is given here as your IDEX.RS is one of the source registers, IDEX.RT register RT is the other source operand. So this is the second instruction which is sitting in your IDEX buffer. Now the earlier instruction will be available, it has finished execution now, it will be available in your EXMEM buffer. So the destination register which is available in your EXMEM buffer should not match with any of these source registers. So that condition is EXMEM.register.RD is equal to IDEX.register.RS or it is equal to IDEX.register.RT. In both these cases you have a problem. So that is the dependence between the first instruction and the second instruction. Now when there is a dependence between the first instruction and the third instruction, the first instruction has already moved on to the mem write back buffer. So you will have to check whether the destination register there matches with any of the source registers available in your IDEX buffer. So that condition is given as 2A and 2B. So memory write back dot RD register RD matches with either register RS of IDEX or register RT of IDEX. So this is the first case is normally called an execution hazard and the second case is called a memory hazard. So detecting the need to forward only when it is not just the destination register matching with any of these source registers, you will have to first of all check whether a register write is going to happen, and only if your destination register is not equal to 0 in the case of your MIPS. Because in the case of MIPS, recall that our register R0 always holds a value of 0 and you cannot write a fresh value into it. So these two conditions will also have to be checked. Your EXMEM register RD should not be equal to 0 and your mem write back register RD should not be equal to 0 and they should actually perform a register write operation. So checking for those conditions, you identify that there is a forwarding that has to be done. So the forwarding paths have been indicated here. So you find that you have a forwarding unit which has been brought in, you have a forwarding unit which has been brought in here, and the inputs to the forwarding unit are from your EXMEM RD, mem write back RD, your RSRT, all these are given as inputs to the forwarding unit. So the forwarding unit will check all the conditions as discussed earlier, and based on that it will generate forwarding signals, a forward A signal and forward B signal to the two multiplexers which are available at the input of the ALU. So forwarding conditions, you look at two hazards here. The first one is an execution hazard. So if your EXMEM.register write is active, so if you are actually going to do a register write and your EXMEM register RD is not equal to 0, it is not register R0 that you are looking at, and there is a match between the RD register of EXMEM and the source register of RS register for the first multiplexer, then the forwarding path A has to be chosen as 1A. Similarly, if it is a register write operation in EXMEM and it is not equal to register R0, and if your EXMEM RD matches with the other register, which is register RT, other source operand, then give the forwarding path B as 10. This is the forwarding condition for your execution hazard. The second one is called the memory hazard, when as I pointed out, it is a dependence between instruction 1 and 3. So, how do you check that? Similarly, instead of your EXMEM buffer, you look at your mem write back buffer. So, if your mem write back register write signal is active and it is not equal to destination registers not equal to 0, and this destination register matches with RS, that is the first multiplexer's input, then the forwarding logic is set for that is set as 1. Similarly, if it is a register write operation and the destination register is not equal to R0 and the mem write back register RD matches with RT, then the other forwarding logic for the second multiplexer is set as forward B is equal to 0, 1. Now, there is a different case also. Now, look at this case. You have an add instruction which modifies register R1. You have the subsequent add instruction which has a true data dependence here. It uses this R1 value but writes into R1 again, and the third instruction which again uses R1. Now, what will happen between these three cases? Now, the first instruction is a very clear case of a true data dependence. The first instruction, you will have to make sure that you take the updated value for the first instruction and the second. But when it comes to the third instruction, there is actually a data dependence between the first instruction as well as the second instruction. So, there is actually an execution hazard happening here, but what will happen is what is actually needed for the third instruction is the updated value of the second instruction. You can't take the value from the first instruction. If you take the value from the first instruction, it will give you wrong results. So, you want only the latest value to be taken for the third instruction. So, you have two types of hazards that happen here, and we want to use the most recent hazard. Now, in order to ensure that such problems do not occur, we will have to slightly revise our memory hazard condition. So, only forward if the execution hazard condition is not true. So, in this case you also have a memory hazard happening because there is a dependence between the first instruction and the third instruction. So, there is a memory hazard. There is also an execution hazard happening because there is a dependence between the second instruction and the third instruction. So, the memory hazard will be considered only when you do not have this execution hazard, or in other words, if this execution hazard is there, then the execution hazard only will have to be handled so that you will get the updated value. So, we just revise the forwarding condition in order to take care of that condition. So, your memory hazard from the earlier stated condition, we just slightly modify it. So, if the memory write back dot register write is active, that is you are going to write into the register, and your register RD is not equal to 0, and if there is if this condition does not hold good, that is RD does not match with any of these registers, your execution hazard does not hold good, then handle the memory hazard. So, that is the revised condition that we have brought in, and the revised forwarding condition is again indicated, consolidating all that. Now, look at the data path with forwarding. So, we introduce a forwarding unit here. So, the forwarding unit will take in all these inputs, and based on that your forwarding unit will take all these inputs, and based on that it will generate the signals to both your multiplexers, deciding whether it is to forward or not. And similarly, you have the control signals here. So, you also have some extra control signals that will have to be generated the moment you bring forwarding into picture. So, this is for your load use data hazard. As indicated earlier, you will have to make sure that a stall is getting created in spite of the forwarding logic that has to be generated. So, what is the change that will have to be brought in if you have to create a stall in your pipeline? How do you create a stall? Now, for that you will have to first of all check your load use hazard. So, in order to detect the load use hazard, you will have to, this is the condition that will have to be satisfied. If your IFID dot register RS, that is the source register, you will have to check that is a source register, or it is a destination register that matches with your data that has to be got from your load instruction. If there is a match, so if it is a memory read operation, that is it is a load operation, and IDEX dot register RT matches with either RS or RT of IDEX, then you have a problem. So, if the load instruction, if it is a load instruction and the destination register of that matches with the source registers of the subsequent instruction, you have a problem. So, you will have to detect that, stall the pipeline and insert a bubble. So, how do you stall the pipeline? So, in order to stall the pipeline, you will have to force control values in your IDEX register to 0, and your EX, MEM and write back do no operations, they do not do any operations, it is a no op. And you will also have to prevent the update of the program counter happening, because you can't go ahead and fetch the next instruction, and you will also have to prevent the update of your IFID registers, because it will have to stall in the same operation, they cannot proceed to the next stage. So, the using instruction is decoded again, the following instruction is fetched again, and one cycle stall allows the memory to read data for the load instruction, and it can subsequently forward to the execution stage. So, this is how a stall can be created. We have already seen how a stall can be created. So, this stall, the bubble has been indicated here for a load use instruction, or more accurately, if you want to show it more accurately, your AND, the subsequent instruction becomes a no op, because you have a bubble that has been created here. So, this becomes a no op. This instruction gets stalled in ID, ID is getting extended. This instruction gets stalled in the instruction fetch. So, this is the data path with your hazard detection. So, along with the forwarding path which we have already seen, you also have a hazard detection unit that has been brought in. So, the hazard detection unit will take in information from your destination register of these buffers, the source registers of the ID stage. So, it will take into account all this, it will evaluate the conditions that we have already discussed, the execution hazard and the memory hazard, and once it has identified a hazard, you will find that it generates signals, control signals to stop the updation of your program counter, it stops the update of your IFID buffer, so that an instruction gets stalled in the IF stage or an instruction gets stalled in the ID stage. And this will also to check whether it is a load instruction and a stall has to be created, your memory read control signal is given here. So, whatever conditions we indicated earlier, so all those conditions will be evaluated in your hazard detection unit, and accordingly the hazard detection unit will send signals. One more signal that you can notice here is you also have zeros given to your multiplexer here, which forms one more control signal here. So, once your hazard detection signal is activated to this multiplexer, all zeros will be given to all the control signals. So, no control signals will be given to the subsequent stages, so that you do not have any updates happening there. So, stalls will definitely reduce your performance, and but you can't say that I will not go in for stalls, because if you do not stall the pipeline at the appropriate stage, you will get incorrect results. So, if there is no possibility of reducing the stalls, or say for example, if forwarding is not going to help, you definitely have to stall the pipeline. Remember that correct execution is always important, performance comes after that. So, stalls will definitely reduce your performance, but if stalls are necessary to ensure correct execution, you cannot do away with these stalls. The other option is the compiler can arrange code, reorganize the code in order to avoid the hazards and stalls. For that, for the compiler to do this, it definitely requires knowledge of the pipeline structure. Now, the other data hazards which we already know, war and war hazards, are not very difficult to handle, because you know that there is no true sharing of data, and it can easily be resolved by register renaming. So, instead of using the same registers, if you use a different register, these hazards can be handled. And when they are handled by the compiler, it is called software approach. When they are handled by hardware, it is called a hardware approach. And the same hazards can also happen with memory operands, only thing is it is more difficult to handle memory operands. So, to summarize what we have looked at this module is, we have looked at how data hazards can be handled by means of forwarding. So, forwarding needs extra hardware paths and control logic. It may not handle all cases and stalls may be necessary, as we pointed out in the case of a load and a subsequent use instruction. And the other hazards, data hazards, namely war hazards and war hazards, can be handled by register renaming using the software, the compiler or the hardware. It can also be handled by means of reorganization of code, which again can be done by software or hardware. Thank you.